You ever wonder how your phone can understand your voice? Or, how an app like Shazam can pick a song out of a super noisy bar? I mean, it really does feel like magic, right? But behind all that, there's this incredibly powerful mathematical tool at work. It's an algorithm that's kind of like a sonic detective, decoding all this hidden information that's just floating around us. And the whole thing kicks off with a really simple but really powerful idea.
And hey, I'm not the only one who thinks it's magic. I love this quote from Kat Moody, who says the Fast Fourier Transform, or FFT for short, is literally the magic spell that makes our modern tech work. We're talking everything from high-speed data to the little antennas inside your phone. So, okay, how does this spell actually work?
And that, right there, is the big mystery. Think about a complex sound wave. Like music or someone talking. It's just this messy, chaotic jumble of all these different frequencies mixed together. So when you feed that mess into a computer, how in the world does the algorithm know the exact recipe? Like, where does it even get that information from?
All right, so to crack this case, we've got to look at a really fundamental clue. It's a clue about the nature of waves themselves. And honestly, this is the secret that makes this whole thing possible.
Okay, this right here is the heart of it all. It's called Fourier's theorem. And what it says is that any signal, I don't care how complex or chaotic it looks, is guaranteed to just be a bunch of simple, pure sine waves all added together. You can think of it like a cake, right? The final cake might look super complicated, but it's just made from a specific recipe of simple stuff like flour, sugar, eggs.
And here's the part that's just mind-blowing. This isn't a guess, it's not an approximation, it is a solid mathematical fact. Every single complex wave has its own unique, discoverable recipe of pure sine waves. And once you know for sure that a recipe exists, then you can start building a tool to go find it.
And that tool, of course, is our algorithm. But here's the key thing. The FFT doesn't just magically know the recipe. Nope. Instead, it acts like that detective we talked about, systematically investigating the signal to figure out exactly what's inside.
So how does this detective actually work? Well, it's a surprisingly simple process, really. It's almost like a process of elimination. First, it takes in that messy signal. Then, it generates its own pure test frequency, like, say, a perfect 100 Hz sine wave. It multiplies the two together to see how well they fit, how much they match up, and it records that score. Then, it just does it all over again for 101 Hz, then 102 Hz, and so on, testing thousands and thousands of possible frequencies, one by one.
You have to understand, the algorithm is completely blind here. It has zero idea what a guitar sounds like, or a human voice, or anything. It's just a tireless, number-crunching calculator. All it does is report one thing: how much of the pure frequency I just tested matches what's inside the original signal. That's it. If one of those ingredients is in there, it gets a high score. If it's not, the score is 0. Simple as that.
So, after our detective has gone through and tested all the possible frequencies, it's finally ready to present its findings. And this is the aha moment. This is where that jumbled mess suddenly becomes a clear, readable code. And here's what that looks like. That messy wave up top, that's the signal we started with. But that chart on the bottom, that's the FFT's final report. And you can see it plain as day, a huge spike right at the 1 Hz mark. That's the algorithm basically shouting, hey, I checked everything, and I found a massive amount of 1 Hz frequency in your signal. Just like that, the recipe is revealed. But just finding the recipe isn't enough. You have to be able to do it fast. And that word fast in Fast Fourier Transform, well, that's the real stroke of genius here. The algorithm figured out this incredible shortcut that just slashed the number of calculations needed. We're talking about turning a process that could literally take centuries into something that takes less than a second. It's a total game changer.
And this quote really drives home the impact. Scott Dorsey talks about remembering the exact moment this change happened in programming. He saw a comment in the code that basically said, "Old slow method, do not use." It was that sudden. The old way was just gone, obsolete. And pretty much overnight, this thing went from being a mathematical curiosity to a practical, world-changing tool.
And what a world it changed. I mean, once we had this super fast recipe finder, it started popping up, well, just about everywhere. It's woven into the fabric of the technology we use every single day.
For starters, it started saving lives. CAT scans? That ability to build a 2D image from a whole bunch of simple 1D X-ray signals? Yep, that's the FFT at work, turning raw data into these incredible medical images we now just take for granted. Then there's national defense. If you need to track a really fast-moving object with radar, you have to instantly analyze the frequency shifts and the waves bouncing back. And the only way to do that in time, you guessed it, the speed of the FFT was the key.
It even powered our entertainment. I mean, who knew? Apparently, John Carmack used it to handle some of the graphics in the original Doom. From classic video games to processing the sound in today's blockbuster movies, the FFT is kind of the hidden star of the show.
And it even cleans up our world. Anytime you use a filter to get rid of static from an audio file or maybe a scratch from an old digital photo, there's a good chance you're using an FFT. It finds the frequency recipe of that unwanted noise and just subtracts it. Gone. So when you really step back and look at the whole picture, you start to see it absolutely everywhere. From the medical scans that see inside our bodies, to the Wi-Fi signals that connect us to the world, to the digital music we listen to. This one elegant algorithm is just constantly humming away in the background, decoding the secret recipes of our world. You know, what the FFT really taught us is that even the most chaotic-looking things can have a simple, hidden structure as long as you have the right tool to find it. And it really makes you wonder, doesn't it? What other huge, complex problems out there, I'm talking about things like brainwaves or climate data, are just sitting there, waiting for their own special kind of detective to come along and finally crack the code?